In this assignment, we're going to talk about gradient and discharge. We're going to talk about the two together because they're really inherently tied together. And also because while you guys are going to go out and measure discharge, I'm not going to have you guys measure gradient because it requires too much technical pieces of equipment, but you guys will still get a conceptual overview here and in your assignment as well. So we'll start out with gradient. By gradient, I just mean slope. So you probably have seen signs on the side of the road that say like, caution, 5% slope. And it's exactly the same concept in a river. It's basically looking at how steep your channel is. We looked at gradient before when we were doing habitat unit delineation. So if you recall back to that lesson, the definition of a riffle is a part of the river that has greater than 1% gradient, whereas a pool and a run has less than a 1% gradient. So we've already been kind of introduced to the topic. Mathematically, it's basically just solving triangle angles. So we have the angle here, that's going to be our actual gradient measurement. And to determine that angle, we're going to need to get rise over run. The nice thing about habitat assessment is that there's not a lot of math associated with it. So we're actually not going to solve for this angle right here. Usually you're just taking the measurements and you're handing it off to someone else and they're doing the math for you. So if you don't like math, habitat assessment might be the area for you. But conceptually, this is basically what we're looking at here, where this would be our bottom of site and this would be our top of site. So we're saying how steep is our river channel? Is it super steep or is it just a little bit steep? When we look at it on our river here, so we have our bottom of site and our top of site. When we're looking at rise over run, so those triangular measurements, we don't need to actually measure run because that's just the site length. We're going to know that from our transects, which we laid out earlier. So we already have our site length, we already have the run. All we really need to do in the field is look at rise, which is just elevation change. That's looking at what the difference in elevation between your top of site and your bottom of site is. You can kind of think of this like stair steps, right? So if you had the elevation change of your flight of stairs, you would take the elevation at the bottom of the stairs and the elevation at the top of the stairs. And from those two pieces of information, you can get the elevation change. Is it a meter? Is it 2 meters? Is it 3 meters? So basically, how high is the top of site versus the bottom of site? So again, when we are sampling for gradient in the field, all we're measuring is the elevation change here. There are different ways to do this. If you want to be super exact, you can use a total station shown here on the left. You've probably seen total stations on the side of the road. They're mainly used in construction, but they're starting to be used more and more in stream surveying. I used total stations a whole lot in my last job. We used to do gradient measurements with them. And the way they work is you have a scope on a tripod. This is like super level, so you level this out. This total station here sends a laser to this prism on a rod here, which is also leveled out. The prism reflects it back, and this little piece here wiggles up and down. And so from the angle of this scope and the angle that the laser is returned, you can get gradient, so that slope measurement. You usually see total stations associated with restoration actions because there's usually more money associated with that. You're not going to see like a nonprofit like NC using total stations very much. Each total station is like $10,000 to $30,000 each. They're super expensive. They're also really giant. They're hard to lug out into the field. I mean, you're setting this up literally in the middle of a river channel. And also they can be difficult to use. As a side note, though, surveying is a really handy skill to have. So if you guys ever have a chance to take like an intro to surveying class, it's really handy in the habitat assessment world. You can also use an inclinometer to look at gradient change or slope. For an inclinometer, you just look through this little eye hole here. And when you move this up or down, this weight here is basically going to swing and tell you what your angle is. Inclinometers are also available as apps on phones. They're a really popular way to do a very like general rough gradient estimate. You're normally not going to see people using these for an entire site gradient. There's a lot of error associated with them. Although if you're doing a very low-tech habitat survey, you might. A lot of times you're going to see people use inclinometers for things like habitat unit delineation. So is it 1% more or greater than 1% or less than 1%? You also might see people use inclinometers when you're looking at like bank steepness, things like that. And then the third way you can do gradient, which is the way that we do in class, which is called using a hand level. So a hand level, you look through this end here, there's a little level bubble here. And so you're leveling this out and you're looking at some sort of like a depth rod or something that has a measurement on it. And if you are exactly level, you're reading, so if you're holding this at like 1.3 meters up to your eye and you're looking straight across level and you're reading 1.3 meters on the depth rod, for example, that means that you're standing perfectly level. You're going to read lower or higher depending on whether you are lower or higher than the depth rod. So that's how we measure gradient. But again, I'm not going to have you guys actually measure gradient for your assessment. I just wanted to give you guys a general overview. So why is gradient important? Gradient is actually super important for a lot of different reasons. One of the main reasons is that it's tied to water velocity. So when we have increased gradient, so you have a really steep river channel, you're going to have water being pulled by gravity more, so it's going to run faster. This makes intuitive sense. When you have a really steep channel, water is going to like run really fast downstream. When you have a low gradient channel, it's going to be a lot slower moving. That relationship between gradient and water velocity shapes a lot of different parameters in your river. For example, when you have increased water velocity caused by high gradient streams, you're going to have larger substrate size. That water is moving fast enough that it's going to sweep away the fine sediment. All that's going to be left is larger substrate size. We saw this with riffles versus pools and runs. You typically have larger substrate size in riffles compared to pools and runs. It goes back to that increased gradient, which causes an increased water velocity. You're also going to see less lateral movement and increased down cutting when you have increased water velocity. So if you picture a stream in the headwaters that's very, very steep, those are pretty straight and they tend to erode down in the riverbed. That's why you get these really steep valleys with a little river running through the middle of it. When you're down in lower gradient areas, like down towards the mouth of rivers, you're going to get more lateral movement, so side to side movement, less movement down, so they tend to erode to the side. That's why you get meandering, and that's a byproduct of the fact that there's lower water velocity near the mouths of rivers. Other things that you can get, you kind of infer from water velocity and gradient are woody debris, for example. So if you have high water velocity, it's going to sweep a lot of that woody debris out of your system. And also fewer pools and more riffles. And that's a product of a lot of different things. One is woody debris. So woody debris is a major factor in forming pools. If you don't have a lot of woody debris, you're not going to get as much scouring. But also because pools are really created a lot of times through channel complexity, things like meanders. A lot of time there's a pool on the outside bend of a meander, for example. Most of the time when you get a very straight channel that's high gradient, high velocity, you're going to get more riffles because it's very steep, that large sediment size, and it's just going to be moving downstream really fast. So this is why gradient is important. Just from knowing gradient, I could make a whole bunch of different extrapolations on where that river probably is, what sort of substrate that river has in it, what the woody debris situation looks like, what the habitat unit looks like, whether it's straight or meanders. So basically gradient is kind of like a master measurement that influences so many different things that it's just really important to take because you can infer a lot of information from it. The measurement that you guys are going to take this week out in the field is discharge. By discharge, I just mean water flow. So I don't really know why, but in the freshwater world, we say discharge instead of flow rate. So discharge, flow rate, they're the same thing. So we're talking about here is what quantity of water is moving downstream and how fast. And discharge is going to tell us information about our stream. Like, does it look like this, where it's tiny, maybe a 10 CFS river, or does it look giant like this, a lot of quantity of water moving downstream? And we measure discharge in the freshwater ecology world in CFS, cubic feet per second. I know you guys typically use gallons per minute in the hatchery, but usually in river sampling and stream sampling, you're doing CFS, cubic feet per second. And you can picture this as a foot by foot by foot square. How many of those fit across your channel, and how many of those squares are moving downstream per second? So it's just a volume per time. There are different ways that you can measure discharge. The most common way that you're going to measure discharge in river systems is the area velocity method. So if we have area of our channel and we multiply it by the velocity, how fast our water is moving, that's going to tell us discharge in CFS. So again, velocity is how fast the water is moving. And typically for that, you're going to use a velocity meter. This is what our velocity meter at the Perry Center looks like. It has a little propeller down here at the bottom that spins that tells you how fast your water is moving. And then the computer up here can report it in meters per second or feet per second. So it's going to tell you how fast your water is moving past you. The other piece of information you need is the area, and that's a cross section. So if you have a raceway, beautifully drawn here, we have a raceway here, the area would just be the width times the height. If you had a pipe, it would just be the area of a circle. Now in a hatchery setting, we're usually working with circles, so pipes, we're working with rectangles, raceways. It's a lot easier to calculate area. When you start talking about the area of a river cross section, it gets a lot more complicated because rivers are not perfectly square and they're not perfectly round. So it's a lot more difficult to measure the area of a river. So instead, what we do is we cut the river up into tiny little sections, and we would calculate the area of this section, the area of the next section, the area of this section, and that's going to give us a good approximation when we add all of these little rectangles together for what the area of our river cross section is. Now, again, the nice thing about habitat assessment, there's not a lot of math associated with it. So as a technician, your job is going to be to measure velocity, so how fast the water is moving, and you're also going to take water depth measurements, which is going to allow you to get at the area. But in my experience as a technician, you're not going to be asked to actually calculate channel area. That's going to be someone else's job who does more of the mathematical side of things. So as a technician, you're just going to go out and you're going to take depths at 15 to 20 intervals on a cross section. So you'll have your channel width, and then you'll take multiple depths across your channel. You'll record those. And then you'll also record water velocity. You give that information to your supervisor or whoever in your organization that calculates it, and they're the one that actually calculates it. So again, not a lot of math, but you do need to understand the basic concept. So that's what you're doing when you're doing the depth measurements in the field. For depth, you guys are able to do that just fine. You'll use your depth rod. For velocity, since you guys don't have access to a velocity meter, we're going to do an alternative method where instead of using a velocity meter, you guys are going to measure out 10 meters of your stream. So there's a known length. And then you're going to drop a buoyant object like an orange or a piece of twig at the start, and then time how long it takes to go 10 meters downstream. And from that information, you're going to be able to get how fast your water is moving.
When you're picking a place to do discharge, you want to pick a place that's a pretty U-shaped channel, but it's not a pool. So that pretty much leaves runs. So runs, like we're in right here, are the best place to do water velocity or discharge measurements. You also want to try and find an area that's pretty straight. So here we have a pretty straight channel. There's not a curve, and you want to avoid sampling just downstream of bends in the river. So this is really a perfect example. U-shaped channel, smooth flow. There's not a lot of stuff in the way that's going to mess with water velocity, and it's a really long segment of a straight channel. So in order to calculate discharge, we need two pieces of information. We need the water velocity, which is how fast the water is moving, as well as the area, so the area of the river channel itself. We'll start with the velocity. You can definitely do this using a velocity meter, and that's the way that most people take discharge measurements. However, a low-tech way to do it, which is what you guys are going to do, and also a way that I've done it in the past when I've had to hike really far into a site and just couldn't carry the equipment, is by using a buoyant object instead. So what I've done is I have a piece of flagging. It's kind of hard to see, but there's some blue flagging there. And I've measured 10 meters downstream to a second point, which I flagged there. What I'm going to do is I'm going to drop something that floats in the water at the upstream end, and then I'm going to time how long it takes to get 10 meters. And from that, I can determine the velocity, meters per second. You can use really anything that floats. An orange is excellent, and also you can eat it for a snack afterwards. I'm just going to use a piece of twig that I found, or wood or something. Piece of flagging is fine as long as you can get the garbage out of the river. Basically anything that floats. So we're going to drop it there. We're going to time how long it takes to get to our second flag. So I'm at my upstream flag. I have my buoyant object. I'm going to drop it in the water and see how long it takes to go downstream. So we'll drop it, and I would start the timer and just watch it as it goes downstream. It's kind of hard for you guys to see though, but I can see it. Okay, so it took my little piece of twig 14.5 seconds to go from the top of my discharge cross section to the bottom. So basically, because I know that these are 10 meters apart, if I want to get meters per second, I would just take 10 divided by 14.5. So that would give me 10 meters in 14.5 seconds. If I divide 10 by 14.5, that's going to give me meters per second. So it's going to be 1 meter in 1.45 seconds. So 10 divided by 14.5. So that gives us the water velocity, how fast the water is moving. But the other piece of information that we need to know is the channel area. So just like in a hatchery setting, where if you determine flow in a pipe, for example, if you guys recall, we had to do the area of the pipe where the water comes out or the area of the raceway, and the area times the velocity gives you the flow. Same thing as a discharge. So just like in a hatchery, we also need to know the area of our cross section. So we'll do the upstream cross section. And basically what we need to know is what the area of this channel is. So if you did a slice right there at our top cross section, what would that look like? Now, the nice thing about habitat assessment in general is that there's not a lot of math associated with it. So this is a really complex riverbed. There's like little nooks and crannies. It's not a pipe. It's not a square raceway. And so we don't, as habitat technicians, actually calculate the area of this channel. All you're going to do is measure the area across. So measure the area across the channel here, and then we're going to take multiple depth measurements throughout the channel, and then we're going to take those depth measurements and take that width measurement, and we're going to send it off to someone smarter than us, and they're going to do the calculations and determine velocity. So again, we're just measuring the length and then taking multiple depths. You guys won't be able to measure the length, so you can just estimate, or the width. You can't, you don't have the surveyor's tape, so you can just estimate the channel width. For this one, we want to do just the wetted width because we're just measuring the water right now. For the depths, just divide the channel visually up into like 15 to 20 different sections, and you're going to take a width measurement from the bottom of the riverbed to the top of the water surface in those equally spaced intervals, 15 to 20 intervals, and that's going to give you an overall profile of what the river cross section looks like.